Recording as we go. So, introduction to quantum numbers. So, this is something that when you read the Schrodinger equation or you look at the solution, it evolves into something what we call as quantum numbers for hydrogen atom. And these are numbers which define any an electron in terms of the energy it has, in terms of the momentum that he has, what you call angular momentum, and its magnetic properties, and as well as its spin. So if you were to at a very higher level, if you were asked about what are the four quantum numbers, then these are, we write them as a set, N, L, M, S, where each one of them means something. N is called principal quantum number, which talks about the energy of, which helps us calculate the energy of a particle. Particle, again, we're talking about electron here. And the relationship is En equals to Z squared E naught over N squared, where E naught is an energy state, is a basic, E naught is the base energy, 13.6 electron volt. And then that N is what gives us orbital quantum number. So the L ranges from, uh, is n minus 1, simply stated. So it's 0 to n minus 1. And it's called orbital quantum number. And what it gives us is orbital angular momentum. So we can calculate angular momentum from that. Now, you have to remember here we are talking about wave particle properties, both of them. So we're talking about momentum here. And from L, we can then calculate what is the M. So M is magnetic quantum number, which we use to find angular momentum in Z direction. I'll show you, if you look at a particle in 3D space, around, going around the nucleus, what would these number mean? And as from our discussion where we started was the quantization uh, of photons that come out of it. So these values have very discrete specific numbers, specific values. So when we say angular momentum is quantized in magnitude and direction. So if you're dealing with a scalar, then with just value, but when we are dealing with a vector, then its direction is also very precise and quantized. Like for Z, we say this can be in any direction, but it will be always parallel to the magnetic field. And then there are other requirements like bound state energies are negative when they're bound. If they're not moving, then we take their energies to be negative because energy is supposed to be uh, calculated from this relationship minus Z squared E naught over N squared. Now, when we say the energy, why does it depend only on N, which is principal quantum number? Because there is a spherical symmetry. They are always in that symmetrical space somewhere. So they'll always be dependent on N and cannot have uh, any arbitrary number or value to them. Now, if you talk about principal quantum number, and this is, we know it now that there are energy levels, energy states, and if a particle goes from higher energy state to lower energy state, like it's shown here in the with this dark green lines, bunch of particles may be jumping from N5 or N4 or N3, they're coming to N2. And what do they do when they do? So, for example, this one photon is shown on the right side, and its HF is E3 minus E2. So simply stated, its energy is the difference of these two energy levels. So for every photon that results from any transition, the difference of that energy would be the energy of that photon. And same, like there's another photon shown on the red, and its energy is E2 minus E1. So now we can put N and L in perspective. So when L is a value which is N minus 1, if N is 1, there can be only one L, right? Which is, and as N goes further and further, you get more values for L depending on that, right? So this uh, kind of a graph can help us see that why does it mean that L depends on N, or L's values range with respect to N. If we take it further, the orbital quantum numbers are then up to, uh, we use them S, P, D, F, G, and so on, and they are what tells us the slight variations in the energy within one band. So what the word that we were using, subbands. So L is telling us that there are within one energy level, within n is equal to 1 or n is equal to 2 or so on, there will be very small differences within that band. And they may belong to S, they may belong to P, they may belong to D or F. So these are the spectral subgroups. And we normally, we are always confined to up to F. Now, when you write then the electronic configuration for one band, we write it like this, 3p6. Now, where the first number is principal quantum number, p is the uh, your orbital quantum number, and then how many electrons are in that orbital quantum number, or that suborbitals, which can be defined by SPDF. So that superscript value tells you how many electrons are there. So now, and we'll get into that. You have seen that before, but today we are trying to understand 1s2 or 2s2, 2p6. What is the significance of p there, or the superscript numbers that come with that? Now, the third one, the m, what you call magnetic quantum number. So this gives us the angular momentum in z direction. So everything that's going around and around has an angular momentum. But the question is that now an electron are moving in different suborbitals. They all will have different uh, angular momentum because of that. So z gives us the idea of what is the angle with respect to the central axis for those. So that is then, because momentum, it's it's a vector, so it has a notion of direction with it. So this is something that helps us find out the angular property, sorry, momentum property, the mass property of that particle. Now, why does it matter? It matters because if you remember Pauli's exclusion principle, no two electrons can have same, or can occupy same space. So they all would have distinctly different values for them. And quantum numbers help us put this into practice. So what does that mean is, for example, if you just stick to hydrogen, which is n is equal to 1. So their things are easy, right? So we have one n, and there's no L, right? So you don't have too many, just one state. So you have allowable, there are two states because spin can be up and down. So one up, one down, so they can coexist. But what happens if you get into uh, complex atoms? So helium, for example, has n is equal to 2. So there can be, if you were to look at a particle with 2n, 1l, and it may be one same value minus 1 for 3, but when you get to the spin, one would be up and one would be down. So it perfectly fits the requirement of Pauli exclusion principle that they can never have exact same quantum values. Now this puts a very good uh, control over every particle in a system. So when you are dealing with one atom in open space, yeah, they can have all these different values of quantum numbers. But when you bring them together and atoms are sharing electrons with each other, this condition helps us make sure that each electron is distinct, and it does not matter which atom that electron belongs to, because now all those atoms are so close that you cannot distinguish which electron belongs to which atom, but you can distinguish which electron belongs to which suborbital, and that becomes more important when we are talking about device and the transport of particles in device. I think I've gone a very important concept in very small, very quickly. So do you follow me that when you bring more than one atoms, 1,000 atoms together, like in crystal lattice for solid silicon devices, they all are sharing electrons. It is not important at that time, or it is not even feasible for us to find out which electron belongs to which atom, because all those atoms are sharing those electrons, right? So more important at that time is to find out which orbital, or what is the quantum number for one electron, right? Because then uh, the, you can identify it by its four quantum numbers, and that's the most important thing at that time, because orbitals are now shared, electrons are jumping from one orbit to other, the locations become important, or the states, those specific locations with specific quantum numbers, they become more important. All right, so let's see. So there's in, let me make sure I got it. So in table 2.1, 2-1, so we see that there are various combinations, and those combinations can help us make sense of which electron has what combination of four quantum numbers. And this, when extended to bigger atoms, we follow the same process or same approach. And this again, not something that you have not seen before, but what I would like you to point out that every bigger atom, you can just explain it in terms of simpler atoms. So if I were to look at say helium, helium is simple. Let's look at lithium. So lithium is atomic number 3, which means you can just put the helium model and then add one more on top. That would give you lithium. So don't get confused when it says helium core 2 electrons. All we are saying is that you can just take the helium as is when you're writing the configuration down, and everything else is the same for up to here. All you're doing is you're adding more orbits on top of those basic designs. So, and then if you have completed the second orbital as well, and now we are going into um, an atom with 3 orbitals, then you can just use neon core, this one, which is up to here, all 2 orbitals filled. You can just say this is that model. On top of that, then there is third uh, orbit, or and so on, and then you fill your third orbit, and this is 2-2. So don't be confused when you see it written like this. All we are saying is, instead of writing the whole configuration, we understand it in a way that, yeah, it can be explained in the simpler model of a smaller atom where all the orbits are filled, and then so on and so forth. And but now the question is that for one atom, we can write it like this. What would happen if you bring in bunch of different atoms close to each other? For that, we have to look at a slightly visual way of how things are. In one atom, you have nucleus and then you have electrons going around. And this figure is just showing that there is, you have 14 protons in the nucleus. So you have 14 electrons around it, right? For silicon. So you can place them 2 in the first orbit, then 8 in the second orbit. Then in second orbit, you have 2 suborbitals, right? And then you have 4 in the third orbit. And in 4, you see then there's again 2 orbits. Instead of making them discrete 3 orbits, we are showing you suborbitals now for each orbit. For one atom, for any electron, if you look at it, the further away from nucleus it has higher energy, right? So now going from that graph that I had, I want you to visualize it. Now let's go back to this graph. So from this chart where we had put like just dashes and we say, okay, you jump from higher energy level to lower difference of energy. I want to say now, can think about it in 3D and actually how these electrons are moving around. There are some identifiers which are written here: inner orbit, excitation. I say ignore that for now. We'll come to these. But right now, my goal is that to build up for what's coming next, I want you to think about three-dimensional way where the further an electron is from nucleus, it has higher energy, right? Now, if I can write it in a 2D way, this should be the way where I say, okay, the center is the nucleus, and I say, I show the distance going apart, and on y-axis is my energy level, on x-axis is my distance from the nucleus, right? Makes perfect sense. Everybody with me on this? So now what we are doing is we are looking at 2 dimension. We have made a 2D representation of that 3D model. And all we want to do, hold on a second. Sorry about that. I don't know how to disable call on this laptop. Anyway, so what we are doing is we are looking at electrons, their positions with respect to the energy. And when you say energy, we're talking about Coulombic potential, right? So it's the electrostatic pull. You have positive charge in the center and you have electrons. For them to stay around, they have to possess energy so they don't fall into nucleus, right? Bohr's model. Now, if we're talking about one atom in free space, it was okay. But now what if I bring 2 of these close to each other? That's what is now we are getting close to what actually happens in a solid state device. And this is where then we see that these orbits or suborbitals, they have to be modified. But that's the next chapter. Today, I wanted to bring up to the point where we look at this figure and we understand and absorb that in it, if I plot it 2D, this is how it would look. For electron to jump from higher energy to lower energy, it has to come closer to nucleus, and that energy, the positions that are there at lower energy are fewer available positions. Those available positions are many more at higher energy, right? Because then you have more orbitals and suborbitals there, right? So this is the takeaway, because we'll